Do you see it now?
Yes. Okay, so
Yeah.
digital to analog converter?
No. Wait. Let us see how this works.
Mm-hmm.
This is an example for demonstrating the computational and control powers of microprocessors, because microprocessors were primarily not intended as a computational tool, but it's rather a control tool.
Okay.
So what does this do? Okay, here it goes. Okay. We want to measure the unknown resistance X. Okay.
Okay.
We want to measure this unknown resistance X. So we're going to output some data from the D to A converter.
Mm-hmm.
This is D to A converter. We can output this. Oh, this is a microcontroller, by the way. This is your chip, or your, that's your output port. Output port is here. Mm-hmm. You're going to send data to your output port, to the D to A converter. You're going to have a physically D to A converter. Mm-hmm. I'm not asking you to purchase a D to A converters or anything. I'm just saying this is one possible application. You see? You don't have to build a project like this or anything. It's just a possible application. You can send the data from here to the D to A converter. You're going to send the digital, is going to convert it to analog. So you're applying an analog voltage here at the input of this amplifier. All right. You're going to read that voltage here by the mux. You're connecting this. Okay, so the voltage here is going to depend on that resistance, right?
Yeah.
Because the ratio between V2 and V1 is equal to R over Rx.
Right.
So if we know R already, then we're going to determine Rx.
Correct.
Now, we know V1 because we already applied V1. But we don't know V2, so we need to measure V2. So this is applied to mux channel 0. We're going to use an A to D converter to read the value of V2.
Okay.
So this is an end of conversion, and you're going to have a start of conversion pulse coming from the microprocessor. You're going to have an end of conversion pulse coming from the A to D converter. Mm-hmm. You're going to have the data of the A to D converter going to the microprocessor. So you're going to read that value, that voltage, by the microprocessor, right?
The data bus. Okay. Mm-hmm.
So what have we accomplished so far? We have applied an unknown voltage V1, known voltage V1. Mm-hmm. We know the value of R from the beginning. Right, yeah. And now we have measured the value of V2 via the A to D converter. Okay?
Mm-hmm.
All right. How did we measure V1? We measured V1 by selecting the mux. We selected, well, let me organize my thoughts better and tell you the story very succinctly from the beginning. Mm-hmm. We apply a voltage V1 to this combination. We want to measure V1 and we want to measure V2. Okay, let me summarize the situation. You want to measure V1 and V2, right? If you measure V1 and V2 and you already know R, then you will be able to determine Rx. We want to agree up till now. Hearing nothing, we are not in agreement so far. Okay. Let us agree.
Okay.
Let me ask this. If you know V1 and V2 and R, are you going to be able to determine Rx, the unknown resistance?
Yes, we can.
Good. So if you know V1 and you know V2
Yes, yes.
and you know R, you will be able to determine Rx. It's a simple equation. Right. How do we know V1? We're going to measure it. Look,
Right.
we're going to measure it by applying this to channel 1. How are we going to know if this is channel 1? We're going to select it by the mux under microcontroller control. We're going to select a bit from an output line here, an output port. We're going to say 1 here. We're going to say 1 here. So it's going to select that channel.
Okay.
So you're going to be able to have V1 appearing here at the input of the A to D converter. If V1 appears at the input of the A to D converter, you want to measure it. So we're going to start a conversion process here under microprocessor control. And then at the end of it, you're going to read the data here, digital. And you're going to convert the digital to analog. So now all of this process was to measure V1. Come up with an algebraic, a single number to represent V1. Now, we want to repeat the same thing for V2. V2 is connected to channel 0 of the mux. So we're going to apply using the microcontroller, logic 0 here. We're going to select this channel, V2. V2 is going to appear here at the output of the mux. You're going to read it by the A to D converter. And then, so the accumulator, the machine or the Dragon or whatever is going to have 2 values now. We have read the value of V1 and we have read the value of V2. And we know R, so the only unknown left is Rx. So can't you consider this to be a resistance meter? Can't you consider this to be a resistance meter?
Yes.
Yeah, it is a resistance meter. It measures resistors.
Right. Yeah, you can.
You can take a picture of this one because this one is not anywhere. You can take a picture of this one and just entertain yourself with it. And it's a demonstration for utilizing the microprocessor computational and control power in impedance measurement, for example, or in measuring of electronic quantities.
Right.
Rx is an unknown resistance. It's like Wheatstone Bridge, where I'm just giving you a simple problem like Wheatstone Bridge. But that's not a bridge. That's a simple computer automated measurement procedure.
Right.
Yeah, that's all. It's an automated measurement procedure that demonstrates the power of the microprocessor in accomplishing things that would have been tougher or more difficult or even impossible to accomplish without the microprocessor. So that gives you the feeling of the appreciation for the microprocessor by seeing similar examples like this.
Professor, I have a question. What is that an 8-bit or what
Yeah, yeah, that's right. That's an 8-bit bus.
Okay, got it. Data bus.
Yeah.
That's right? Or
yeah,
address bus.
Yeah, just take a picture of that.
I did.
And just enjoy it, I would say. Just take a picture, and if you have a chance to use it to make a project like this, be my guest. But I don't know how you're going to do it.
You have to buy the analog to digital converter? Is that like $5?
Let me tell you, it's not easy to be a project because of the present situation and the distance learning situation. So it's not going to be an easy thing to do under the circumstances, but at least you know the theoretical concept behind it, that it can be done. It is 6 o'clock now, and we have already borrowed a few minutes from Samson, unfortunately, but well, I'm glad that we're done with chapter 5, and then we're ready to start chapter 4, I should say, and we're ready to start 5 next time. Next class, which is Wednesday, we're gonna attack 5 and 6. I don't know how much we will finish from 5 and 6, but we will do the best we can, you know. You're welcome. Okay, everybody. Have a good evening then.
Thank you.
Bye.
Okay, Professor, can I say something here?
Yeah, go ahead.
Hi, so guys, may I have your attention? So since we just finished the lecture, so let's just take a quick break and we will start the lab section at 6:10, okay?
Okay.
Good.
All right. Okay, then see you guys in 6:10. All right, thank you. In another Zoom meeting.
Thank you, Samson. Yeah, we'll see you.